Hello, my name is Xavier Devroy. I'm an assistant professor at the University of Namur in Belgium, and in the next few minutes I will present the result of using basic block coverage as a secondary objective for unit test generation at the SBST 2022 tool competition. Basic block coverage is a secondary objective that addresses the problem of implicit branches, like runtime exception, when trying to generate a test. Let's take an example. Here is a method under test coming from the XWiki project, an open source enterprise wiki system. When using a white box search-based unit test generator, the method under test and the related dependencies are provided as input to a generator that will usually apply a genetic algorithm to produce a set of tests covering each line of code. To evaluate how close a given test is to covering a target line of code, the algorithm will use two metrics. The approach level measures the distance between the execution path of the generated test and the block of code containing the line. And the branch distance measures the distance between a test's execution and the coverage of a true or false branch of a particular predicate in a branching statement. For instance, assuming that we try to cover line 409, the generator will create an initial population of test cases. When executing the different tests, they will cover the different statements of the method. If the current tests do not enter the for loop, we have test cases with an approach level of 2 and a branch distance between 0 and 1. However, the approach level and the branch distance only check control-dependent nodes. This means that if we have implicit branches, like for instance null pointer exception thrown at line 404 or 405, the fitness value of the corresponding tests will be the same. So what can we do to address this issue? In their work, Fraser and Arcuri propose to use testability transformation to make implicit branches explicit. The general idea is to pre-analyze the code and instrument it to add additional instruction to guide the search to cover implicit exceptions. The main limitation of this approach are the extra cost of the pre-analysis and the difficulty of detecting implicit branches in classes used directly or indirectly by the class under test. Instead of using pre-analysis and testability transformation for unit test generation, we defined a new secondary objective called basic block coverage, which was presented and evaluated in our paper recently accepted for publication in the Empirical Software Engineering journal. The intuitive idea is that basic block coverage can be applied when two test cases cover the same blocks but trigger implicit branches along the path to the target line. In such a case, the two tests will have the same approach level and branch distance. To decide which test to select, basic block coverage zooms in on the partially covered basic block and looks at the line coverage of the two tests. If one test covers more line than the other, this test will be selected. For the unit testing tool competition, we used our implementation of basic block coverage for Java programs. This implementation has been done on top of EvoSuite. We configured EvoSuite to use DynaMOSA with two secondary objectives to maximize the basic block coverage and minimize the test length. We set the usage rate to 0.5, meaning that whenever two tests have the same fitness value, there is a 0.5 probability of comparing the basic block coverage of the test. We also set the sleep time to 10 seconds, meaning that there is a delay of 10 seconds before using basic block coverage for each new target added to the active list of targets during the search. Our implementation of basic block coverage is openly available on GitHub. From the result of the competition, we see that in general, the lines and conditions coverage increase for basic block coverage when the time budget increases. However, we see a decrease in the mutation score. We will further manually investigate this decrease by looking at the generated test. One possible explanation could be the difference in the number of generated tests, more than 18,000 tests in total across the different runs for 30 seconds time budget, against only a bit more than 15,000 tests in total across the different runs for 120 seconds time budget. As expected, the results of basic block coverage are close to the one of EvoSuite, which is also in line with our previous evaluation of basic block coverage for unit test generation. There is, however, a difference in the coverage and mutation score of the different benchmarks between EvoSuite and basic block coverage. The tool seems to cover the benchmarks differently, and this difference seems to evolve over time. Further investigation is needed to identify the factor influencing the effectiveness of basic block coverage for a specific benchmark, like for instance the presence of different kinds of implicit branches and the sleep time for small search budget. More information about basic block coverage for search-based crash reproduction and search-based unit test generation are also available in our preprint. If you are interested in our work, do not hesitate to look at the other topics we are working on and reach us by email or via social media. This work has been partially funded by the European Cosmos Project and the Cyber Excellence Project funded by the Walloon region.